Hey, I've got a bet for you. It's a classic, one that sounds super simple but has been stumping people for decades. It's a fantastic brain teaser that shows just how wrong our intuition about probability can be. So, you ready to test yours?
Okay, here it is, the big question. Picture this. You're in a room with 29 other people, so 30 people total. What do you think the odds are that at least 2 of them, any 2, share the exact same birthday?
Go ahead, really think about it. Pick a number, lock it in your head. Now, if you're like most people, you're probably guessing something pretty low. Maybe 10%? 20? It just feels like it should be rare, right? Well, let's find out.
I'm not going to spoil the answer just yet, but I will tell you this. It's a lot higher than you probably think. And to really understand why, we need to grab a couple of key concepts first. Think of it like building our probability toolkit.
Okay, our first tool is all about understanding the difference between 2 kinds of probability scenarios, independent and dependent events. I know it sounds a little jargony, but getting this right is absolutely crucial to cracking this puzzle.
Let's break it down. Independent events are things like flipping a coin. The outcome of one flip has absolutely zero impact on the next one. But dependent events, they're different. Think about picking people for a group photo. Once you've chosen someone, they can't be chosen again. The pool of options actually shrinks with every single choice you make.
Let's make this really concrete with an independent event. Imagine a simple 10-question multiple-choice test. Every question has 4 possible answers, A, B, C, or D. Your answer to question 1 has no bearing whatsoever on the answer for question 2. They're totally separate.
So, how many different ways could you answer that test? Well, it's 4 options for the first question, times 4 for the second, times 4 for the third, and so on, 10 times. That gives us this massive number, over 1 million possible combinations of answers.
And this really shows the power of compounding probability. The chance of any one specific answer key, say getting all C's, is just 1 out of that huge total. The odds are, incredibly slim.
All right, time for our second tool. We're going to shift gears from those independent events to dependent ones, where suddenly the order of things becomes absolutely critical.
So here's our new scenario. We've got 8 people on a waiting list. What do you think the probability is that they get called in perfect order, from the youngest person straight to the oldest?
Let's just walk through the logic. The probability of calling the youngest person first, well, that's 1 in 8. But once they're called, they're out of the pool, right? So the chance of calling the next youngest is now 1 in 7. Then it's 1 in 6, and so on all the way down until there's only 1 person left.
This type of calculation, where the order is everything, actually has a special name. It's called a permutation. The total number of ways you can arrange these 8 people is 8 factorial, which is just a fancy way of saying you multiply 8 times 7 times 6, all the way down to 1.
And that gives us a grand total of 40,320 possible arrangements. Since only one of those is the perfect youngest to oldest order, the probability is a tiny 1 in 40,320. So the big takeaway here is this. When order matters and the options decrease, the number of possibilities just explodes. Remember that idea? Exploding possibilities.
All right, toolkit's ready. We understand independent and dependent events. Now, let's go back and finally crack the birthday problem. This is the fun part.
Now, you might be thinking we've got to calculate the odds for every single pair of people in that room. That sounds like an absolute nightmare, and frankly, it is. But luckily for us, there's a much, much smarter way to solve this.
And here it is, the indirect method. This is a really clever trick in probability. See, instead of trying to calculate the odds of something happening, sometimes it's way easier to calculate the odds of it not happening. Then you just subtract that number from 100%. So let's apply this. The event we actually care about is at least 2 people share a birthday. The exact total opposite of that is no 2 people share a birthday, meaning everybody is a completely unique one. So we're going to calculate the odds of that much simpler scenario first. This calculation should actually feel pretty familiar. It's a dependent event, just like our waiting list example. For the first person, there are 365 days they could be born. For the second person to have a different birthday, there are only 364 days left. For the third, 363 days. And you do that for all 30 people. So what are the odds of that chain of events happening?
The probability that all 30 people have a unique birthday is only about 29%. Just let that sink in for a second. In a room of just 30 people, it's actually pretty unlikely that everyone has their own separate birthday. This right here,
This is the secret key to solving the whole puzzle.
And now for the final, super simple step, we just use our indirect method. We take the total, 100%, and we subtract the probability of the thing we don't want, which is that 29% chance that nobody shares a birthday.
And there it is. The probability that at least 2 people in a room of 30 share a birthday is over 70%. So, how close was your guess? It's not a coin flip. It's not even close. It's a very, very likely event. This is an absolutely fantastic bet to make, as long as the other person hasn't seen this explainer, of course.
So that leaves us with one last question. Why does that answer feel so wrong? Why is our intuition so incredibly off the mark when it comes to this problem? Let's break it down.
Okay, the main reason is that we frame the question wrong in our own heads. We hear shared birthday, and we immediately think, what are the odds someone shares my birthday? But that's not the question. The question is about any 2 people sharing a birthday. In a group of 30, you're not just checking 29 other people against yourself, you're checking every single possible pair. And that number isn't 29, it's a whopping 435. With that many different chances for a match to happen, that high probability suddenly makes a whole lot more sense.
So I'll leave you with this final thought. A tour guide has a group of 27 tourists. She bets them that at least 2 people in the group share a birthday. The tourists think the odds are totally in their favor. But you know the secret now. You know how quickly those pairs add up. So, would you advise them to take that bet? Yeah, I think we both know the answer to that one. Thanks for diving into this with me.